Okay. So in the last class, did we explore all the four rules? Did we go for Aufbau's rule? No, no, we didn't. No. So we just could finish this one, the configuration, right? Okay. So now we will follow up with we'll go for the electronic configuration. Okay. So right now we know the details, right? How in the various shells, for example, in the first shell, okay, there is only one subshell named S, which has got only one orbital, which has got only two electrons in it, right? Second shell will have S and P subshell, namely L is equal to 0 and 1. And S subshell will again have one orbital, P subshell will have three orbitals. So it will be 1 plus 3. Each orbital will have two electrons. So that means it is going to be totally 8. Fine, ma? Third shell likewise will have N is equal to 3. So L is equal to 0, 1 and 2. And therefore they will be having S, P and D. Okay. And S again has got only one orbital. P will have three orbitals and D will have five orbitals totally. So 1 plus 3 plus 5 is 9 and 9 into each orbital 2 electrons, so 18. So this much we know. Likewise, it will keep increasing. The next one will be 2n square. You can accommodate totally 50 electrons. The fourth shell will accommodate the 50 electrons totally. Sorry, 32 electrons. 2 into 4 square, so 32 electrons. Okay. So there the orbitals, the subshells will be S, P, D, and F. One orbital in S, two electrons. Three orbitals in P, so six electrons. Five orbitals in D, so 10 electrons. And seven orbitals in F, and therefore 14 electrons. So sum it up, and that becomes now 32. So this way you can keep writing the electronic configuration. I mean, at least the subshells details and the orbitals details. Now we know what is there within a shell. There is a subshell. That subshell can have one orientation, can have two electrons. Within the second shell, there is S subshell, one orientation, two electrons. P subshell is dumbbell shaped and it has three orientations. Each one of them will contain two electrons, so totally six electrons. So if you look at S subshell of any shell, it will contain a maximum of two. P subshell of any shell will contain how many? P subshell of any shell, 6. D subshell of any shell, L is equal to 2, na? So plus 2, plus 1, 0, minus 1, minus 2. 5 orbitals into 2 electrons, so totally 10, right? And F Vishak, how much? What happened? Hmm. Yeah, Vishak, when did you leave? Okay. So in F subshell, how many electrons can be there, Vishak? 14. Okay. Right. So now there are some rules to be followed while writing the electronic configuration. We know within the shell what is there, etc. So now we are going to fill them with the electrons. Okay. We are going to scatter the electrons and we are going to write, in other words, the electronic configuration by following the rules to be followed. Okay. So what are the rules? The number one rule, which is same as the rule given by Bohr in class 9, saying that the first shell is first filled up, and until the first shell is fully filled up, you do not go to the second shell. Remember that? Until the inner shell is fully filled, we will not give the electron to the outer shell, right? Same thing here is said to be Aufbau's rule. It is said to be Aufbau's rule. Okay. Aufbau's rule says that filling up of various subshells or orbitals, we can put it as orbitals, takes place in increasing order in increasing order of their energies. That means the orbital with the least energy should be given electron first. Then progressively the orbitals with the higher energy will be receiving the electrons. Okay. Okay. In increasing order of the energies. That means lower energy orbitals will be given electron first and then the higher energy orbitals. Okay. Now, this rule is quite understandable, but now who will tell me which has got lower energy and which has got higher energy? So there should be some criterion na, to check the energy of the orbital, right? Or the subshell. Rule is what? The filling up of the electrons. Electrons will go into the lower energy orbitals first, and then they will enter into the higher energy orbitals. But who should tell me which has got lower energy, which has got higher energy? For which there is a rule called as N plus L rule. Okay. What does it say? It says lower the N plus L value, lower the energy. And in cases where the N plus L value is same, in cases of same N plus L value, okay, the lower the N value, lower the energy. Is it okay? Lower the N value, lower the energy. So first we will check the N plus L value of the subshell or the orbital. Lower the N plus L value, lower the energy. If the energy is lower, we will go for Aufbau's rule and fill the electrons in those orbitals first. Then we will go to higher orbitals. Supposing while calculating the energy by N plus L rule, two of the subshells or orbitals receive same N plus L value, then you will go for the lower N value, lower the N value, lower the energy. Is it clear? Can we apply it now? So in the first shell, we have got only S subshell, right? In the first shell, we have got only S subshell and nothing else, right? In the first shell, we have got only one S. In the second shell, we have got two S and two P. So the 2 here refers to the shell number, or it also refers to the principal quantum number. The S will be indicating the azimuthal quantum number. When you see S, that means L is equal to 0. Is it right? Okay. Any problem in this? Okay. Then in the third shell, we will have S, P, and D. In the fourth shell, we have got S, P, D, and F. Progressively, it keeps increasing. So 5S, 5P, 5D, 5G, 5F, and 5G. That means in order to have a G subshell, what should be the minimum principal quantum number value? Should be the minimum principal quantum number value in order to have a G subshell would be 5. So only in the fifth shell do I find the G subshell. Only in the fourth shell do I find only in the fourth shell do I find the F subshell. Okay. Only in the third shell onwards do I find the D subshell and so on. So let us fill it up. Okay. After that, you've got sixth shell. So 6P, 6D, 6F, 6G and 6H, let us say. 7S, 7P, 7D, 7F, 7G, 7H and 7I. I'm just writing. Okay, then 8S, 8P, 8D, 8D, 8F, and so on. Okay, now what we will do is we'll go with the N plus L value calculation. So I'm going to use a very light color to calculate N plus L value. What is the N plus L value of 1S? N value is 1. And what is the L value for S? 0. So that means, isn't it 1 plus 0? What will be the N plus L value for 2S? It will be 2 plus 0. Okay. What will be the n plus L value for 2p? We know L is equal to 0, 1, 2, and 3. S, P, D, F. So what is the L value for P? 1. What is the N value here? 2 plus 1. So 3. So this will be 3 plus 0, 4 plus 0, 5 plus 0, 6 plus 0, 7 plus 0. Is it okay, children? And this will be 3 plus, sorry, Vishak is not there. Huh? He came, okay. What happened, Vishak? Okay. So 3D, we will say 4, 3 plus 2, na? Correct, Vishak? Okay. So likewise, we can say 4 plus 2, 5 plus 2, 6 plus 2, 7 plus 2. And here it will be 4 plus 3, right? 4 plus 3, 5 plus 3. This is 5 plus 2, 6 plus 2, 6 plus 3. Okay. Comfortable with this? 7 plus 3 and so on. So now, if you look at the orbitals, which has got the least n plus L value? 1s. So we'll first give the electron to 1s. After 1s, what will you do? The filling up of the electrons happens in the, yeah, we'll go for 2s. Okay, so 2s. Then after 2s, 2p. Then after 2p, okay, actually here itself, what happened you see? If any two orbitals or subshells have got same n plus L value, isn't it? 2p and 3s. It's 2 plus 1 and this is 3 plus 0. And both of their n plus L values are 3, na? So when you have same n plus L value, in cases of same n plus L value, lower the n value, lower the energy, correct? So according to this, which has got lower energy? The 2p or 3s? 2p. So we'll go give the electron to 2p. Then come to 2p, then after that 3s. Then after 3s, after 3s, 3p. Now incidentally 3p and 4s have got same energy. 3 plus 1. Yeah, no, lower the n value. If you have same n plus L value, then lower the n value, lower the energy, no, Shaq. Yeah, 3p, then 4s. So you should note one thing that the third shell, so we filled up the first shell, second shell, but when we move to the third shell, we filled up to 3p and suddenly we are going to 4s. We are not going to 3D, right? Why are we not giving electron in 3D as compared to 4s? Yeah, 3Ds, n plus L values 3 plus 2, 5. Right? Just give me a minute. Right. So what we do is we give the electron to 3p and after that 4s. Once 4s, is it going to 3D or something else, children? After 4s, where will we go? After 4s, where will we fill electrons? 3D. So after that 3D. So why 3D has got 5? After that, we'll go to 4p. So this looks very random. So what we do is we have people have generated a shortcut for all of this. What shortcut is that? What they do is they draw a line like this. Okay. So they go for 1s first, then 2s, then 2s, 3, 2p, 3s, then 3p, 4s. After 4s, where do we go? 3D. After 3D, where should we go? 4P. After 4P, do we go to 4D or do we go to 5S? So that means after 3D, we'll go to 4P, 4P to 5S. So are you able to read the pattern? Once you put these lines, it automatically satisfies the rules. It automatically satisfies the N plus L rule. Okay. Okay. This is a shortcut of you don't have to sit and write the electronic configuration by every time counting and rearranging. So this pattern helps you to automatically write. So we'll go to 1S and then we will go to 2S. After 2S, we'll go to 2P. After 3S, we'll go to 3P and so on. Fine. So if I go for electronic configuration of something like potassium with atomic number 19, potassium has got atomic number 19. So what would be the configuration, come on? Can we put it as 1s2, 2s2, 2p6, 3s2 and 3p6? So far 18 electrons. This is basically argon's electronic configuration. After 3p, where will we go and how many more electrons are there? After 3p, which orbital receives electron and how many? And it would get only one. Is that fine? And that means the inner 3D remains. In the 3D, in the third shell, the 3D remains 0. It is not occupied. Okay, calcium, which is having atomic number 20. So can we see these 18 electrons as such, followed by 3D 0 and 4s2? 1s2, 2s2, 2p6, 3s2, 3p6. That would make 18. 18 plus 2 more in 4s, keeping the 3D vacant. Is it okay? But once 4s has been filled up, where will we give the electrons? So can you predict scandium's electronic configuration with 21 atomic number? We can actually put calcium as argon followed by 3d0, 4s2. Every time if you don't want to write the entire electronic configuration, we can just code the previous inert gas. After that, whatever extra electrons are there, that we will write separately. So argon has got 18 electrons. So tell me for scandium. Hmm. 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 Yeah. Okay. So can we put it as argon followed by 3d1 and 4s2? Okay. Now, supposing we say, I told you, no, these 18 elements, 18 electrons, how many electrons are there in argon? What will be the electronic configuration of argon? Isn't it 1s2, 2s2, 2p6, 3s2, 3p6? So we will say, yeah, you can write fully. 1s2, yeah, you should. See, when you have big elements, I'll just show you the periodic table. And supposing you are writing now the electronic configuration of the 21st element. Think about when you are writing for something like 100th element. Will it be possible for you to write fully? It is possible, but won't it be tedious? Yeah. So what we will do, we will take the previous inert gas configuration and we will say that it is fully filled. And after that, whatever extra electrons are there, we will put. The previous inert gas. The previous inert gas. For example, look at this. There is the periodic table is completely based on the electronic configuration. Okay, so I feel you will be able to understand. You both will be able to understand. It should not be a problem. Otherwise, I won't do it here. Normally, we do it in periodic classification of elements only. So if you see, uh, this is, one minute. See, there was hydrogen, which is not visible because of this AI2. So hydrogen is 1, 1. So this is 1s1. Helium is 1s2. S is completely filled. Lithium is 1s2, 2s1. Beryllium is 1s2, 2s2. Boron is 1s2, 2s2, and 2p1. Atomic number is 5. So 5 electrons. Progressively, the P is capable of holding 5 more electrons. Na? The P is capable of holding 6 totally. Already in boron, 1 is there. So what will be carbon then? 1s2, 2s2, 2p2. 1s2, 2s2, and 2p2. Nitrogen, 1s2, 2s2, 2p3. Oxygen, 2p4. Fluorine, 2p5. Neon, 1s2, 2s2, 2p6. Can you read the pattern? In argon, will it not be 3p6? In krypton, it will be 4p6. In xenon, it will be 5p6. So supposing I want to write the electronic configuration of cesium, okay, which comes after xenon. It's the 55th element. What will I do? I'll put it as xenon and followed by the 6s1. So up to xenon, the electronic configuration will remain the same. After xenon, one more electron. Xenon's atomic number is 54 and cesium's atomic number is 55. So compared to xenon, which has got 54, the cesium has got only one extra electron. So imagine, no, you are writing for atomic number 55. So you'll have to finish. Let us write. Nothing wrong. Let us write, shall we? For cesium. See, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 3d10, 4p6, 5s2, then 4d10, then 5p6, and then 6s1. That would be the configuration of cesium. How many electrons in cesium? 55. Just count whether you have 55 electrons. This is 10, 18, 28, 38, 48, 54, 55. Correct, children? So it is becoming difficult for us to write so much. And most importantly, the chemical properties of an element will be decided by the valence shell, outermost shell. We have got nothing to do with the inner shell, na? So better to put them all as xenon's configuration followed by sixes. Is that fine? Okay. So anyhow, coming to titanium with 22. See, 1s2, 2s2, 2p6, 3s2, 3p6. So far it is 18 electrons. Configuration of argon is over. Configuration like argon is over. After that, what? How many more electrons? 18 plus 4 more. So we'll say it is 4s2 and 3d2, right? Okay. Now I'm going to ask you a question. What will be titanium plus 1 configuration? How does titanium form cation? Hmm. Now, what did you do, Vishak? You removed the electron from the third shell. Is it fair? Which is exposed to the outside world, fourth shell or the third shell? Then, so normally, how do we write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2? But actually, you should know that the 3d is part of the third shell. Whether you write it this way or that way, nobody will consider it as wrong. Because 4s is the one which receives the electron first, then 3d, right? But You want to put the third shell's components together? Nothing wrong. Now, when you remove the electron, where from you will remove? The fourth shell or the third shell? Where always it is outermost shell. So from the fourth shell, I'll remove. That means the configuration will become 1s2, 2s2, 3s2, 3p6, 3d2, no change. And this will become 4s1. Is it okay? This is going to be one of the most common question that you will face. Okay, write the electronic configuration of, let us say, Mn plus 2. So first let us write Mn. Mn is 25. Manganese is 25. Atomic number is 25. So 1s2, 2s2, 2p6, 3s2, 3p5, 4s2, 3d5. But is the 3d really located in the outermost region? We filled 4s first, then only 3d. But that doesn't push the 3d to the outer place. Na? It's still part of the third shell. So if you want to remove the electron, you will remove from so configuration will become 1s2, 2s2, 2p6, 3s2, 3p6. Sorry, why did I write 5? I don't know. And this will become 3, 4s0 and 3d5. Removal of electron always from the last shell. This number tells you the shell number. So fourth shell will lose the electron. Clear? Yeah, we shouldn't omit. We are informing that the electrons have been lost from the forest. Huh. Yeah, see, Vishak, it is, even if you write like this, there is technically nothing wrong about it. If you have missed the 4s0, technically you are right only. But you are highlighting the fact that, yes, ma'am, I removed it from the 4s. Got it? Nothing wrong. Nothing wrong. Even if you stop by saying 3d5 and don't quote 4s, it's all right, I'm saying, as long as it conveys the message. Fine. It depends upon sometimes the teachers who correct the papers. Okay, they may require, oh, why you have not written for us? Even though it is zero, you should have written. All these things you will see. See, board correction, class 12 correction is going to happen in a very different way. But class 11 is your school specific. How your school wants your paper, it should be in that format. So learn the concept. But when the teacher says in the class that you should write, you shouldn't write, or you need not write, follow whatever they are saying. Class 11 is all about concepts. Okay. And it's comparatively, I wouldn't say tough, but if the same syllabus was given to class 12, the score would come down actually. You can now compare your 9th standard and 10th standard syllabus, which was comparatively harder. Recollect the physics lesson in 9th standard. Yeah, tougher. So in 12th standard, you will feel it is comfortable. Okay. It is bulk. Moreover, in 11th standard, you would have endured the portions. You would have got some maturity level na, by looking at so many concepts. So when you go to 12th standard, the things can be acquired more easily. That is also one thing that makes 12th comparatively easier. Okay. So portions wise, 12th is volume. See, in class 11, we need to focus on the concepts. In class 12, we need to focus on the book because you are going to score from it. Board exam, na? So you have to go through each and every line. Even now, 11th standard, you should go through, but the concepts are much deeper. Okay. So in class 12, the biggest challenge will be organic. All other chapters are discrete, 5 different lessons, totally 10 lessons. And before COVID, remember it was 16 lessons in 12th standard. Okay. So after COVID, after rationalization, you face 10. out of which in organic, there are 4 lessons which are continuous. So that's the biggest challenge in 12th standard. Other lessons are discrete. Okay. So 11th is all about conceptual understanding. So do that, and in any competitive examination, okay, specifically in NEET, it is NCERT. In JEE Mains, it is NCERT only. And chemistry will be the maximum score provider to you. I'm not saying because it is my subject. If you ask any senior who has attempted the JEE paper, they will say I scored maximum in chemistry because it is very close to the textbook. And those who ignore chemistry will definitely go down. Okay. So it's more of concepts. So Adanala, what I'm saying is whether you should write or should not write. Technically, it is not wrong to leave it. But whether you should write or not depends upon your chemistry teacher. She says you write, you write. She says not, it's okay, don't write, don't write. Is that okay? Okay. Shall I proceed? Okay. So we learned 2 rules. And with the help of these two, that is filling up of the various orbitals will take place in increasing order of their energies. And how to identify the energy? The energy will be identified by N plus L rule. Okay, lower the N value, lower the N plus L value, lower the energy. Out of the two who have got same N plus L value, lower the N value, lower the energy. Okay, coming to the third very important rule, which is called as Hund's rule of Hund's rule of maximum spin multiplicity. Okay, Hund's rule or simply Hund's rule, or you complete it and say Hund's rule of maximum spin multiplicity. So what does it say? Now, I'm going to write the electronic configuration of some elements. Say, for example, I'm going to write it for copper, zinc. Okay, at the end of it, at the end of maybe today's class, we will discuss about the abnormal electronic configuration of copper and chromium. Okay, I gave you homework, I believe, right? To write the electronic configuration. Did you write? Hmm. Okay. So did you write copper and chromium in that? Did you write copper and chromium? If you had written from up to zinc, you would have written. What did you write for copper? Why 4s to 4p6 men? Okay, anyway, we'll come to this copper and chromium story later. Okay. Okay. So I'm hoping that you both have done the work. Zinc's atomic number is 30. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. Agreed? 30 electrons. Okay. Fine, children? Okay. Now, I'm going to see what is the shape of this. Can we put it as spherical? And there are 2 electrons in it. S is also spherical. Now, P, we know it's dumbbell. So there is a px, there is a py, and there is a pz, right? So these are the 3 orbitals of P. Then comes the S, spherical. Then P, you will have again dumbbells. And D is more complicated. Remember, did we give the names to them? Did we do the shapes? No, we have not done. Okay, it's more complicated than P. We'll do that in the next slide. Okay. What are they? We'll complete this. So instead of drawing these diagrams, we draw a box diagram, which is easier to depict. The orbitals do not look like boxes at all. This is only representation. So S subshell has only one orbital, correct? which is capable of holding two electrons. This S also has got one orbital. The S subshell will have one orbital, two electrons. P subshell has got how many orbitals? Three. So what I'll do is I'll put the three like this. Then again comes the 3s, one orbital. 3p, again three orbitals. D, how many orbitals? How many orientations? So I'll put the like this. 1, 2, 3, 4, and 5. Then again 4s. This is called as box diagram. If I want to avoid the orbital diagram, I can use this. This provides some more clarity. So in the 1s, there is only one orbital containing two electrons. And the two electrons should have different spin. Na? One with plus half and the other one with the minus half, right? So I will depict the plus half as an upward half arrow and minus half as a downward half arrow. Is that fine? Then 2s. Okay. Okay. Ah. So 2p, what will we do? We will say there are six electrons. So 1, 2, 3. Are you seeing how I'm doing? 4, 5, and 6. Okay, I could have done it in a different way. 1, 2, 3. That's wrong. Okay, or I could have done it like this. 1, 2, 3. That's also wrong. Okay, so what do I mean? Okay, which rule am I following? I'm following the Hund's rule of maximum spin multiplicity. Okay, let us come to that. But before that, can you understand that there is a gap between the 1s and 2s? In the box diagram, I've left some gap between 1s and 2s. I've left some gap between 2s and 2p. But I've not left any gap between the 2p orbitals, na? Which means all the three orbitals have same energy. And this is supposed to be degenerate. When orbitals of the subshell have got same energy, we can call them technically to be degenerate. All are at the same energy level. So do you think the 1s and 2s are also degenerate? If they were degenerate, I should have joined their boxes, na? The fact that I am giving a space indicates that the energy of 1s is different from the energy of 2s. The energy of 2s is different from 2p. The energy of 2p is different from 3s. Energy of 3s is different from 3p. But the three orbitals of the 3p have got again the same energy. That means they are degenerate. So when I'm not putting a gap between the five orbitals of D, that means all the five orbitals are degenerate. Okay. So what is the rule now? Rule says when you are giving electrons in the degenerate orbitals, we should ensure that each of the orbital is singly filled with parallel spins. Once all the degenerate orbitals have received one electron each, then pairing begins. Is the statement clear? Pairing of the orbitals in the degenerate orbitals, pairing of electrons, pairing of electrons in degenerate orbitals does not take place until all the degenerate orbitals receive one electron each with parallel spin. What do you mean by parallel spin? I cannot be having, I told you, remember, this is a wrong way of filling up. Plus half, minus half, plus half. Are they parallel? Are all of them parallel? Parallel in sense, are all of them having same spin? We did fill all of them singly, but do all of them have got same spin? Yes, Vishak, clear? Okay. Now, why so? Why do we need that? It is to ensure that there is maximum spin multiplicity. Okay, Hund's rule is telling us to pair the electrons in the degenerate orbitals only when all the degenerate orbitals have received one electron each with parallel spin. And why? So, in order to ensure that there is maximum spin multiplicity. Now, what do you mean by maximum spin multiplicity? Supposing I'm writing the electronic configuration of nitrogen. 7 is the atomic number. I would say it is 1s2, 2s2, and 2p3, right, children? So 1s has got 2 electrons, 2s has got 2 electrons, and 2p is now going to have 3. So in what way should I put? What are the various ways? What are the various ways? I can put them in 1, 2, 3. So am I not having 3 times the plus half spin? So 3 by 2 is the total spin. What if I do plus half, minus half, and plus half? What will happen? Then I'll have 2 electrons with plus half and 1 electron with minus half. So I'll be left out with only half. No? The plus half of 1 electron will be cancelled by the other. So what you will be left out will be 1 plus half. Is it giving me maximum spin multiplicity? No. So do not do like that. Okay, what if I fill like this? Check. What will be the maximum spin that I can avail from this? Vishak, how much is the maximum spin that I can avail? 4. 4. Huh? Come again, please. So that will get cancelled now. And this will be still left. So that means it is plus half, na? Okay. We could have filled the electrons like this. It would be 3 times minus half. Okay. And it's all right to do so. The negative spin is no way less than a positive spin. Do you get my point, children? Only thing is, traditionally we fill the electrons first with plus half with positive spin, and traditionally we fill the electrons after that with minus half spin. Traditionally, nothing wrong in saying even this, children, because negative doesn't have any other meaning other than indicating the spin. So quantitatively, a clockwise spinning electron is same as anti-clockwise spinning electron. So what rule have we followed? When you have to give electrons to the degenerate orbitals, you ensure that each of the degenerate orbital has been given electron, 1 electron each. And if you have to pair up, then start pairing up only after giving electrons, 1 electron to each one of the degenerate orbitals. Is the rule clear? Is the rule clear? Shri, okay. That way, I can also write the electronic configuration of nitrogen saying it is 1s2, 2s2, 2px1, 2py1, and 2pz1. Why? We know that when it is p subshell, p6, I mean p subshell, okay. That is L is equal to 1 will indicate the p, and m values will become +1, 0, and -1. So there are three orbitals, right? What were their names? Did we not say px, py, and pz? So when you have one electron each, we can say px, py, pz. This will be further more detailed electronic configuration of nitrogen. Any doubt in this? Vishak, clear? So what will be the electronic configuration of oxygen in detailed form? Come on. S2, 2s2 and 2p. And where are these four? Isn't it in 2px? How are they? 1, 1, 2, and 3. Once each of the degenerate orbital has been given one electron, now you start pairing up. Na? So it will be 1, 2, 3. Now you have the rights to pair up. So that means it is 2px2, 2py1, and 2pz1. Are we clear? Okay. Now coming to d orbital, L is equal to 2, the d subshell. So ml values would be +2, +1, 0, -1, -2, right? And they should have some names, no? They should have some names. The names are, what happened to Vishak? He left and joined back, is it? What happened? The internet problem today. Okay. Okay. So there are 5 orbitals in the d subshell, namely dxy, dyz, dzx, dx square y square, and dz square. If S was spherical, P was dumbbell, do you think D will be a simple structure or a little more complicated? So dxy, okay, this is x-axis, y-axis. The d orbital comprises of 2 lobes, one here and one here. Okay, so on the xy plane, so we'll put it like this. On the xy plane, you have got 1, 2, 3, and 4. Or basically 4 lobes and 2 dumbbells. Clear? That's on dxy. Now, the dyz will be y-axis and z-axis. Now, again, the dumbbells are in between the axis lines. Is it fine? This is y, this is z. dzx. This is z-axis, this is x-axis. So, lobes are in between. Sorry, ma? I didn't get your question. Even this is 3. Oh, you have a basic doubt. Even the S was a 3D, it was spherical. Even S is spherical. But what we can do on the paper is a 2D diagram only, no? Understood? So all these are spaces. How can spaces be flat? Spaces have to be 3-dimensional, na? What did I say? Did I not say ML values are orientations or orbitals or space? Nobody will use this term in the book, but they are actually the regions where the probability of finding the electron is maximum. So they are spaces, and spaces must be 3-dimensional. What we are drawing is only a 2-dimensional picture. Fine. Okay. No. What is there to be solved? So it will be like this. And so sometimes what they do is this looks little different. No? So what they do, they'll say this is Y, this is Z. So they rotate and put it on the paper. and they will indicate like this, same as this, but only labeling will be different. So this also can be, this was X, this was Z. So we'll put it as X, this is Z, though Z is not actually there. And we'll just labeling will only differentiate the three from one another. Okay. Then comes dx square y square. These are very peculiar ones where the lobes are located on the axis line. In all the previous ones, the lobes were actually in between. Now the lobes are actually on the axis line. Is it okay? The dz square looks even more different. It's located on the z axis and there is a disk in the majority of the lobe is located on the z axis. This is located on x and y. And there is a disk of electron density. Is it a disk? Is it a three-dimensional object? Again, I'm asking you. Is it a boundary? We are talking about the regions inside the atom. So do you think an atom will have a wall made up of, or a boundary made up of some matter? No, no, no. So what we have done is actually when we do quantum mechanical model, na, say for example, I'm doing the quantum mechanical model, studying the oneness. Okay. We are not going to do much in quantum mechanical model. So an S electron around the nucleus can be found here, can be found here, can be found here, here, anywhere like this. The pattern of their uh, availability is like this. So what we do is, oh, the electron can be found here, electron can be found here, electron can be found here. We are talking about probability. Can one first shell, S subshell, have so many electrons, children? How many electrons are there in S? But I've done so many dots. These are nothing but plots. Where the electron is, I am going to put a dot. Okay. In next instance, the electron is going to move around. No, electron is not stationary. So it will be found somewhere else. It will be found somewhere else. So what we are doing is we are collecting all those plots and we try to draw a boundary surface diagram to include most of the points where the electron is found. And that looks like a sphere. So it was indeed a three-dimensional structure. Okay. Right. So D is indeed a three-dimensional. D, Lame, the three-dimensional. So shapes of orbitals. See, these are all three-dimensional. And F, imagine F. F is still more complicated. This is S. The first one is S. It's radially symmetrical. Imagine a football. The P, it's located on PX, PY, and PZ. Fine? PY and PZ. Then this is the D. D. Fine? Is it okay, children? Four lobes. Where are they? It is present between X and Y plane. So this must be XY. Can you see four lobes? This is what we were drawing as four lobes in a simplified manner. See, this is basically what? This is Y and this is Z and this is X axis. So the lobes are between X and Y. So we used to draw like this. Okay, these are the four lobes. Clear? So these are the three-dimensional shapes. Okay, so D, X, Y, Y, Z, Z, X. This is dz square. Okay, so 5 of the d orbitals. Now look at the F. There are 7 orbitals and they look even more complicated. So we will not attempt to draw. Is it okay? So we will learn only the shapes up to the D. Clear? Okay, the last rule. Let us conclude the last one. Okay. The last one is said to be Pauli exclusion principle. Pauli's exclusion principle. What it says is that no two electrons in an atom can have same set of four quantum number values. In other words, each electron is unique. Correct? Each electron is unique. So I'll take one example to just depict this. For example, if I'm taking helium, helium has got 1s2 configuration, correct? So can I put it as the first electron and the second electron? There are two electrons. I'm going to write the N value, L value, ML value, and S value. It's also called as MS value sometimes. What is the N value for the first electron? Where are they located? What is the principal quantum number value of electrons? Why 2? Helium இருக்கிறதே 2 எலக்ட்ரான். எங்க கொடுப்ப? 1 first ஷெல்லோட S sub shell தான நம்ம கொடுப்ப. Correct? Helium's atomic number is 2. There are only 2 electrons. So will you go straight away and give to 2s? What does this notation indicate? This is principal quantum number. The 1 is principal quantum number. S indicates the azimuthal quantum number. This 2 represents the number of electrons in it. So what is the N value for it, Shri? Is my voice not clear to you? For you also, Vishak? Okay, okay. So what is the principal quantum number of, see, first, what is the electronic configuration of helium? Shri, what is the electronic configuration? Whenever you get the work to do the, so this diagram should run in your mind or you should write it. So where will you give the electron? To the 1s. How many electrons can be given in S? And how many electrons does helium have? So that completes the configuration. Na? What is the meaning of this one? What is this one doing here? And the principal quantum number tells you the shell number, right? So it's present in the first shell. So what is the principal quantum number value of the first electron and the second electron? There are two electrons in it. There are two electrons. I'm trying to write the principal quantum number. Can we say 1 and 1? Both are 1. L value. L value, how would you see? L 0, 1, 2, and 3. S, P, D, F. What is the L value for both? 0. What is the magnetic quantum number, Vishak? 1 na? Oh, where are we? 5 minutes lagging Larkani. 0 and 0. Okay. And MS, the spin. First electron should have plus half. You can put it as just spin quantum number or MS. The other one should have minus half, correct? So don't you think they have their own address, unique address? Can two electrons in helium have same set of four quantum number values? And that is the principle. No two electrons in an atom can have the same set of four quantum number values. Is it clear? Okay, now I'm going to give you lithium. Can you tell me the configuration of lithium? Lithium is the third element with atomic number 3. 1s2, 2s1. Okay, now I'm going to commit a deliberate mistake. I'm going to write 1s3. Okay, so what is the n value for the first electron, second electron, and the third electron? What is the n value? 111. L value? 000. ML values? Okay. Now come to spin value, MS value. What shall I do? I'll give traditionally plus half. For second electron, what will I give? So for the third electron, what should I give? Anything of the two, na? It can either it should be clockwise spinning or anti-clockwise spinning. So it should have some spin. Na? The third electron cannot be stationary. So it can be plus or minus half. So let me say plus half. Now see, by writing 1s3, I committed a mistake. The first electron and third electron have got the same quantum number values. All the 4 quantum number values are same. Is it possible according to Pauli exclusion principle? No. Okay. So in an orbital, how many electrons should I put to avoid this kind of a mistake? 1s has got one orbital. How many electrons should I put in one orbital to avoid this kind of a mistake? Plus half, minus half. Should I put one more? And the moment I put one more, then this electron and this electron will have same set of quantum number values, correct? So where did I go wrong? By putting the third electron into the same orbital. Okay, so that is the mistake. So this is wrong electronic configuration. Anyhow, one more statement can be concluded from this fact. In an orbital, there can be maximum of only 2 electrons. Do you agree with it now? The moment you put a third electron, either you are repeating the details of the first or the second. And no 2 electrons in an atom can have same set of quantum number values. So in an orbital, you cannot have more than 2 electrons. That also is yet another form of Pauli exclusion principle. Clear? Okay. So in the next class, we will start with the abnormal electronic configuration of chromium and copper. And then we will proceed to the beginning of the lesson. Now we know the electronic configuration. Okay. So we will proceed to the first part of the lesson, like how the structure of atom was deduced. Clear? Clear? Okay. Yes, children. Bye. Yes, ma'am. You can leave. Bye, ma'am.